All right, so in order to be able to graph an absolute value function, there's a few things that you've got to know first. And you're going to be introduced to a new formula, and you're going to see this formula over and over and over again, not just in Algebra 1, but when you move on to Algebra 2. You're going to see it for 5 or 6 different types of equations. This is called the general or vertex form of an absolute graph function. The reason why we call it the vertex form is because it tells you what the vertex is. So the vertex is the point where the graph turns. So if you look at this graph here, this is the shape of an absolute value graph. An absolute value graph is always going to be V-shaped. You can see that it makes the turn here at the point 0, 0, or at the origin. So that would be the vertex. What's going to happen is these letters in here tell us where this vertex is going to be. It actually tells us the point where that vertex will show up. Now, when we start with this, the y and the x, we're just going to leave alone. We don't touch the y and the x. Those are always going to be there. The ones that are going to change, the variables that we're going to be working with, are a, h, and k. So what a, h, and k do are this. A is going to be responsible for any stretch, compress, or reflect on your graph. Now, in the ones that we're going to do in the book here, you are only going to have an a value of 1, but I'm going to show you what an a value greater than 1 or an a value between 0 and 1 is going to do to the graph. So if your a value is greater than 1, then your graph is going to end up getting stretched. So that means it gets narrower. Think about taking the rubber band and stretching it out. That's what happens when you get an a value greater than 1. If your a value is between, we've got to do, a is greater than 0, but it's less than 1. If the value of a is greater than 0 but less than 1, then what's going to happen is it's going to be compressed. So it's going to be flattened out. It's going to be like somebody's pushing down on that graph. Now, if your a value is negative, then what that is going to do is it's going to take it and it's going to flip it over the vertex. So instead of opening up, it's now going to open downwards. Okay? And that's what your a value is going to do. Now your h value and your k value, that's what's going to control where your graph is going to go, or where your vertex is going to be located. So what we're going to do is I'll go ahead and put up a new graph here and show you what would happen with specific points. So this right here is what we call our parent function. Okay, it starts at 0, 0, and it has an a value of 1. If we have, say, x minus 3, the absolute value of x minus 3 plus 2, then the h value is going to be the opposite of that number right there. So instead of being negative 3, your h value is going to be 3. What that tells you is that it's going to move 3 units to the right. Now, if this h value, if this were x plus 3, then you would be moving 3 units to the left. The thing you need to remember with the h value is it's always going to be the opposite of what you see. So if you see negative 3, then you have to think positive 3. If you saw positive 3, you have to think negative 3. And you're going to move left and right on the number line based on that value. Now the second part of this is the k value. The k value controls your up and down or your vertical movement. So since this k value is 2, and this is going to be the same as what you see. So whatever you see here, that's what you're going to do. Since this is positive 2, you're going to move up 2 units. So our graph would now look like that. It's been moved 3 units right and 2 units up. And that's why we say this is vertex form, because what we've done is we've moved our vertex 3 units right and 2 units up. And that's going to work the same way whether we're doing quadratics, radicals, logarithms, exponential functions, whatever we're working on, it's always going to work that same way with a, h, and k. All right, so before we move on to the problems in the book, I want to show you the parent function, or the function that we're going to base every one of our translations off of. The translation is simply the movement or the change in the way that the graph looks. Okay? So our parent function is going to be y equals the absolute value of x. And what we can see here is that we have no given a value, we have no given h value, and we have no given x value, or k value rather. So what you would do is, or what you can do if you get confused by this, is you could write it out like this. Y equals, remember that the number right here is being multiplied against the absolute value. So the number cannot be 0, because if you multiply anything by 0, it just works out to 0. So anytime that we're assuming that there's a number out here being multiplied against something, we're going to assume that number is 1. So this is y equals 1 times the absolute value of x minus, and since there's no h value, that is assumed to be 0, and since there's no k value, that is also assumed to be 0. So now this might make it a little bit easier to fill out all the information that's going to be required of you. So we know that our a value is 1. Now if the a value is 1, we automatically know the answer is always going to be, for stretch, compress, reflect, none. There is nothing that we're going to do to this graph based off of the a value. So it's going to look like this, 2 45-degree angles, and that's it. Then we're looking at the h value. Well, the h value doesn't matter that it's minus 0, it's just 0, because there's nothing there. The k value, since there's nothing being added or subtracted to the absolute value, that means the k value is automatically 0. Then your vertex is just going to be taking your h value and your k value and making it into an ordered pair. So we know that the vertex of this graph is going to be at 0, 0. So what I can now do is I can come over here to my XY chart, and you see how I've got this area kind of sectioned off here. This is going to be what I'm going to call later on the axis of symmetry, which we won't cover until we get to quadratics later on, and then the vertex, or the y value of the vertex. So this point is 0, 0. That's going to be the very middle of my graph, and there's a reason why that's important. So I'm going to go ahead and mark that off on the graph here as well at 0, 0. The next thing I'm going to do is look at, do I have a maximum or do I have a minimum? Now, what happens is, whenever your a value is positive, you're always going to have a minimum value. Because what this means, if the a value is positive, your graph is going to open upwards. And so that means that your vertex is the smallest y value possible for your graph. Now, if you had a negative, that means that it gets reflected, and then your vertex point would actually be the highest possible, or the maximum value allowed for y. And so what we now have, looking at this, we've got a positive 1, so that means that we are going to have a minimum. And what I do with these is maximum I capitalize as a capital M, and minimum I do as a lowercase m. If you've ever done music and you know major chords versus minor chords, major's always capitalized, minor's always lowercase. It's kind of the same idea here. It's not an actual math thing, but it helps you to have it keeps you from having to write out max or min or maximum and minimum every single time. Now the maximum and the maximum or the minimum is going to be a minimum at y equals, and then all you're going to do is go to your vertex point. Whatever the y value of your vertex point is, that is going to be your minimum or maximum point. So y is equal to 0. Then the domain. Okay, whenever we're dealing with an absolute value, or at least the ones that we're going to look at, your absolute value is always going to have a domain of all real numbers. So we can just use our symbol for real numbers there. Okay, that means that eventually every single x value moving left to right is eventually going to be touched by that graph. And so that means that every single point is within the domain. Then your range is going to be which y values are going to be touched by the graph. Well, right now we know that our graph starts at 0, 0, or y equals 0, and is going to open up. So that means that our graph is going to eventually hit every single y value. It's never ever going to hit a value below 0. So that means that we have a restricted range. It's never going to go below 0. So we would write this, we can write it a couple of different ways. We can write it as y is greater than or equal to 0, or we can write it as open bracket 0 to infinity and then close parenthesis. And you should recognize this as interval notation. Either one of those is acceptable. So these are all the things that you're going to have to list. This is all the information you're going to have to do. Once you get used to it, you're going to be able to do all of this information in 15 to 20 seconds max. The next part we're going to do is we're going to look at, we really only need 3 x values to be able to graph an absolute value, because what we've got is basically 2 lines that converge. And you know at this point that you only need 2 points to draw a line. But I want you to get used to doing quadratic functions, or get used to this process for when you get to quadratic functions. So I want you to choose 5 points. We've already got 1 point here, so now what we need to do is choose 2 larger than 0 and 2 smaller than 0. What I would recommend is go ahead and just use -2, -1, 0, 1, and 2, because that's going to be the easiest thing to do. And then what we're going to do is we're going to take those values and we're going to plug them in for x and see what the resulting y value is. So if we put -2 in for x, we get the absolute value of -2, which is 2. So when x is -2, y is 2. Plug in -1 for x. When the absolute value of -1 is 1, so when x is -1, y is 1. Come on down here, absolute value of 1 is 1, so we get y is 1. Absolute value of 2 is 2, so then we get y is equal to 2. And you can see that when we have our y's, we have a symmetrical looking, or we have a balance between what's on top and what's on the bottom. And if you do it correctly, you will always see that, that symmetry between them, as long as you don't have fractions. Once we start getting into fractions, then that kind of throws everything off. But as long as you're dealing with integers and you choose the correct points, then you know that you're going to have symmetry on your y values. Now all we do is we take these and we graph them. So -2 and then up 2, -1 and then up 1, 1 and then up 1, and then 2 and up 2. So we're going to go ahead and connect all those together, and you can see that we get this V shape, and that right there is going to be your parent function. Every translation that we do in this class is going to be based off of that graph right there. All right, so in problem number 1, we're going to look at graphing an absolute value function. What we want to do is we want to relate y equals the absolute value of x minus 2 to y equals the absolute value of x, and see what is the difference between the two. So what we're going to take a look at first is, what does the parent function again look like? And we can see that we've got this 1-to-1 relationship on the slope to the right side, and a 1 to a -1 relationship on the slope to the left side. So basically what we have is 2 lines, y equals -x and y equals x, meeting at the origin, and then nothing going below that. Remember that anytime that you've got an absolute value function, you're going to have a V-shaped graph. So in order to figure out what this one is going to look like, let's go ahead and walk through our entire table of things that we need to know. The a value, since there's nothing out here in front of the absolute value, we know that the a value is 1. And whenever the a value is 1, we know that there's no stretch, compress, or reflect. The h value is, there's nothing that is being added or subtracted to that x within the absolute value. So that means that our h value is 0. And then our k value, the thing that's being added or subtracted on the outside of the absolute value, is -2. So we can go ahead and put 0, -2 in here for our vertex, and then we can go over to the graph and we can actually go ahead and graph that point 0, -2. Now the vertex we know is going to be 0, -2, so we've already got that on both the chart and the graph. The maximum or minimum, remember that this is going to be, we have a minimum on this one because our graph is going to be opening up. Since our a value is 1, that means it's going to look like this. So that means we've got a minimum point down here at the vertex. So it's a minimum at y equals, and then the y value of the vertex, which is -2. In our domain, basically whenever we're doing absolute values, especially in Algebra 1, the domain is always going to be all real numbers. So you can come down here Just go ahead and put all real numbers there. Then for our range, we're just going to take y and -2, and then we need to figure out is our graph going to open up above or below that vertex? Since it's opening up above, that means all of our values are greater than or equal to the y value of the vertex. So now we've got all this filled in. We should have some idea in our heads of what our graph is going to look like. So now we're going to take the chart and start filling the XY chart in. So we need two values that are less than 0 and two values that are greater than 0. So I'm going to go -2, -1, 1, and 2. Now remember that with an absolute value, you can actually do just 3 values because you've got basically what amounts to 2 lines. But because we're going to be doing quadratics very, very soon, I want you to get used to choosing 5 different points in order to be able to do what you're going to do with quadratics later on. Now just take the -2 and plug it in for x. So the absolute value of -2 is 2, -2 is 0. -1, so the absolute value of -1 is 1, -2 is -1. We've already got 0, -2, so now we go to 1. Absolute value of 1 is 1, -2 is -1. Plug in 2, absolute value of 2 is 2, -2 is 0, and there you have your XY chart. Now what you again should notice is that if you've done this correctly, if you've got all integers to work with, or if you've got halves to work with, you should end up coming out with the y values that are symmetrical. So you can see we've got 0 here and 0 here, -1 and -1, and then in the middle is -2. Now what that tells us is that we're going to have a V-shaped graph here, or in the case of parabolas, we'll have a U-shaped graph. So go -2, 0, and then -1, -1, and then 0, -2, 1, -1, and then 2, 0. Go ahead and put those together, connect the dots, and there you have the translation. And what you can see is that because we have a k value of -2, what it's done is it's pulled the entire graph down 2 units. So whenever you see a simple equation like this, you should have a pretty good idea of what that graph is going to look like, because all it's doing is taking this parent function and just moving it left or right if there's an h value, or up or down based on if there's a k value. Okay, for problem number 2, all we're going to do is change that k value from a -2 to a +2. And we're going to see the effect that it has on the graph. So again, you can see that I've got the parent function graphed, I've got the parent function listed, and we're going to go ahead and start filling in this information. So again, the a value is 1. We have no stretch compressor reflect because the a value is equal to 1. The h value is 0, but this time the k value is 2. Now remember that in the last graph that we did, the k value was -2 and it pulled the graph down 2 units. So what we should see on this one is, since the k value is +2, it should actually push it up 2 units. The vertex is going to be 0, 2, because all we're doing is taking our h value and our k value and putting it together, so 0 and 2. We can go over here, go ahead and graph 0, 2. Maximum or minimum. Again, we've got an a value of 1, which means that we're going to be opening upwards. Opening upwards tells us that we've got a minimum point. So it's going to be a minimum at y equals, and since the value of y at the vertex is 2, that is going to be our minimum value. Domain is always going to be all real numbers again. And then our range is going to be y and 2, and again, since it's opening upwards, all of our values on our graph are going to be greater than 2, so it's going to be greater than or equal to 2. Once you got all that filled in, now go into your XY chart and just pick some numbers. So again, -2, -1, 0, 1, and 2 are the best ones to use. Plug them in. So absolute value of -2 is 2, plus 2 is 4. We know that the same thing is going to happen down here, so we get 2 and 4. Absolute value of -1 is 1, plus 2 is 3, and we know that we're going to get 3 there as well. So now we can just go over to our graph, start filling these in, and we've got -1 and 3, -2 and 4, 1 and 3, and 2 and 4. Connect them together, and you can see that all that we've done is we've taken the parent function and we've moved it up 2 units. All right, so for problem number 3, we're going to change the k value out and make that 0, and then replace the h value with a new number. So we've got y equals the absolute value of x plus 5. No k value, new h value. So again, we've got the parent function's already been graphed, and go over here and go back and start filling in our information. So the a value of this one again is 1. And since the a value is 1, that means that there's no stretch compress or reflect. The h value this time, remember we're going to go to the opposite of whatever this number is. So since we've got a positive 5, that means that our h value is negative 5. We go outside, this is a plus 0, so we know that our k value is 0. So this time we've got an h value of negative 5 and a k value of 0. So that's going to be our vertex, negative 5 and 0. Go back over here, and you can go ahead and graph this. So negative 1, 2, 3, 4, 5, and there you have your vertex point. Now again, for maximum and minimum, our graph has an a value of 1, which means it's going to open up, which tells us that our minimum point, or we're going to have a minimum point this time, and that minimum point is going to be again at our k value. So the minimum is at y equals 0. Make that look like a 0 and not a 6. The domain, as always, is going to be all real numbers. The range is going to be anything above this y equals 0 or equal to that 0. So we get y is greater than or equal to 0. So again, we filled in all of our information. So now we've just got to go in and choose some x values so that we can figure out what our graph is going to look like. What you want to do on this, in this case, is go 2 numbers smaller than negative 5 and 2 numbers greater than negative 5. So negative 7, negative 6, then negative 4, and negative 3. And again, since I've got 2 units away from 5 and 2 units away from 5, then that means that these y values should be similar or the same. 1 unit away from negative 5 and then 1 unit again away from negative 5, that means that those y values should be the same as well. So let's go ahead and plug this in. Negative 7 plus 5 is negative 2. The absolute value of negative 2 is 2. Let's go ahead and check this just to make sure that we're right. Negative 3 plus 5 is 2. The absolute value of 2 is 2. So we know that these are correct. Negative 6 plus 5 is negative 1. The absolute value of negative 1 is 1. And so I'm going to get a 1 there as well. So now I've got negative 7, negative 2. So I'm going to go all the way out here to negative 7, go up 2. Negative 6 and 1. Then negative 4 and 1, and negative 3 and 2. And again, go ahead and connect all those dots. And you can see that what we've done is we've taken our parent function and we've just slid it 5 units to the left, because that's what our h value does here. Since we have a positive h value, it's going to move everything to the left. All right, so for problem number 4, we're going to go over just a concept here, and this is called a piecewise function or a step function. So in the scenario that we're given in the book, we've got for every 60 students that are going on a field trip, you're going to need 1 bus. So what this shows, what we can do is we can take that information and we can present it onto a graph, because we're comparing buses to students. So here's what we know. If we have 0 students, we need 0 buses. So what we're going to do is we're going to use an open circle at x equals 0 and 1 bus. Then we know that we can fit 60 students on that first bus. So we can come over here to 60 and we can use a closed dot, and that shows us that the 60th student is included on this first bus. And then what we'll do is we'll draw a line from 0 to 60. Then once we get that 61st student, so I'm going to use an open circle again at 60. This time it's telling me that that 60th student is not included on the second bus, so that's greater than 60. So we're looking at the 61st student here. Now student 61 to student 120 can fit on the second bus. So we'll go ahead and put a closed dot at 120 and we'll connect those dots together. Then again, we'll do this for bus number 3. Student number 121 to student number 180 will go on the third bus. So again, what I'll do is I'll put a circle or an open circle at 120 and then a closed circle at 180. And again, what that's telling me is that student number 121 is going to be on this third bus. Student 180 is also going to be on that third bus. And what you would do is you would continue drawing this graph out until you had either exhausted your buses or you'd exhausted your students. And you can see that the way that this works is it looks like a series of steps. That's why it's called a step function.